Okay, today we're going to pick up where we left off after Chapter 2. Remember, in Chapter 2 we talked about risk and return, and that primarily involved individual securities. We did look at a little bit of portfolios, but basically we looked mainly at individual securities. In this chapter, we're going to discuss something known as modern portfolio theory. And this is the theory of how to build portfolios, and in particular, diversification. In other words, risk reduction that you get from building portfolios. So let's review a little bit. In Chapter 2, we saw that the expected return of a portfolio was simply a weighted average of the expected returns of the securities that are in the portfolio. And you might recall that we had an example where we had the two stocks, Blandy and Gourmand, and one of the portfolios we built included 75% of the money invested in Blandy and the other 25% in Gourmand. So if we want to calculate the expected return of this portfolio, one way that we could do it is we could simply calculate period by period a weighted average of the return on Blandy and the return on Gourmand. And so in this case, you can see in the furthest right column, if we take 0.75, that's the weight of Blandy, times 26%, plus 0.25, that's the weight of Gourmand, times 47%, we get 31.25%, and that's the return on the portfolio in period 1. We could do this again for period 2, and 3, and 4, and 5, and so on, until we went through all 10 periods, and what we would have then would be a historical time series of the returns that this portfolio would have earned had we owned it for that entire 10 years. And then if we calculate the average of those 10 returns for the portfolio, we would get 7.10%. Now, there's an easier way to do this because presumably we already know the expected return on Blandy and we know the expected return on Gourmand. So we have 6.4% and 9.2%. And if we calculate a weighted average of those expected returns, as the equation says, we should get the same 7.10%. And that's exactly what we see here. Now, the standard deviation of a portfolio is more complicated. We could do exactly what we just did. In other words, find the historical time series of returns for the portfolio and then calculate the standard deviation of those, just like we previously did for Blandy and Gourmand. So if we do that, we have 31.25% and negative 2.25% and so on. If we take each of those minus the 7.1% expected return, square the result, and then multiply by 1/9 and add up all the results, this is exactly what we did in Chapter 2, we should get 22.16%. But most of the time, we don't have that historical time series of returns, and that's particularly true if we have a large number of securities. So more likely, we know what the expected return for each security is, and we know the standard deviation of each security, and we know, or we could calculate in theory, the correlation between each pair of securities. And if we do that, then we have a formula that we can use to calculate the standard deviation of a portfolio, as you see here. And this formula simply says that the standard deviation of a portfolio is, and this is for two-stock portfolio. We'll see here in a minute, this gets more complicated as you add more and more securities. But for a two-stock portfolio, we take the weight of stock number 1 squared, that might be Blandy, times the variance of stock 1, plus the weight of stock 2 squared, that might be Gourmand, times the variance of Gourmand, plus 2 times the correlation between the pair of securities, times the standard deviation of the first stock, times the standard deviation of the second stock, times the weight of the first stock, times the weight of the second stock, and then take the square root of that whole thing. Now, that probably looks complicated to you, and I'm not going to say that it's not, but it's a whole lot less work than calculating the standard deviation of the portfolio from those historical returns. So let's see how this works. Let's plug in some numbers. So remember that the weight of Blandy is 75% and Gourmand is 25%. So we have 0.75 squared times the standard deviation of Blandy squared, in other words, the variance of Blandy, plus 0.25 squared, that's the weight of Gourmand squared, times the standard deviation of Gormage squared plus 2 times the correlation, and we calculated this in chapter 2, that was 0.11257. So 2 times 0.11257 times the standard deviation of Blandy times the standard deviation of Gormage times the weight of Blandy times the weight of Gormage. Take the square root of all of that, and you get 22.16%. That's the same number that I have in the table there that we could get from calculating the standard deviation of the historical returns on the portfolio. Now, remember that covariance and correlation measure precisely the same thing. So instead of using the correlation in this equation, we can have a slightly simpler version of the equation if we use the covariance. And that's what you see here. So you notice that the covariance replaces the correlation times the product of the standard deviations. And if we plug in the numbers, it's very much like what we did before, except a little bit shorter. And we get, of course, precisely the same answer. Notice that the standard deviation of the portfolio is less than the standard deviation of Blandy or the standard deviation of Gormage. We talked about this in chapter 2. The reason for that is because Blandy and Gormage have a very low correlation. And more specifically, with any two stocks, if their correlation is less than +1, in other words, less than perfectly positively correlated, then you're going to get a lot of risk reduction. The lower the correlation, the more risk reduction you get, or we could say the better the risk-return trade-off will be. Now, I've created a little video at right here that shows exactly how this works. So in this graph, what we have is we have two securities. We have A and B. Notice that A is less risky and has a lower expected return, and B is more risky and has a higher expected return. So the two endpoints of the line there are A and B. All of the points in between are various combinations of A and B. So the point in the middle would be half A and half B. Now, keep an eye on the title of this chart. Notice it says right now the correlation equals 100%, or in other words, +1. This is perfect positive correlation. And what we find in that case is that all possible combinations of A and B lie on that straight line. But as we lower the correlation, we're going to see that that line begins to bow out in the direction of a better risk-return trade-off, which is towards the northwest. So you can see that the correlation is dropping, and at the very end, and we'll look at this here in just a second, at the very end we had a -1 correlation. So let's walk through this. So correlation of 80%, that's less than +1, and so we get a better risk-return trade-off. Notice that the line starts to bow out towards that northwest direction. And if we lower the correlation even further to say 40%, it bows out further. And at 0%, it keeps bowing out. Notice also that points A and B don't move. That's because we're not changing the individual securities. All we're doing is changing the correlation. And as we lower that correlation, the portfolios, the combinations of A and B, get better and better. If we keep going, -20% is better still. -40% is better still. -60% is still better. And then finally, at -100%, this is the best that we can do. Notice something important here. Right about on where y equals 12%, we have a portfolio with 0 risk. That will always be the case when you have two perfectly negatively correlated securities in a portfolio. It's possible, depending on the weights that you choose, to find a portfolio that has 0 risk. In general, though, when you have 3 or more securities, that will not be possible. And the reason is very simple. You can't have A, B, and C all simultaneously being perfectly negatively correlated, because imagine that A and B are perfectly negatively correlated and A and C are perfectly negatively correlated. Well, in that case then, C must be perfectly positively correlated with B. It can't be any other way. And because of that, you can't create a perfect risk-free portfolio with 3 or more securities. Now, we've seen how to calculate the expected return of a portfolio and the standard deviation of a 2-security portfolio. With any number of securities, the expected return works the same way. It's always just a weighted average of the expected return of the securities. However, the standard deviation is more complicated. And the reason for that is that we have to account for the correlation or covariance between each pair of securities. And so we can write out the portfolio standard deviation formula as I have here. Now, I know that the double sum can be a little bit scary, but all this means is that we have however many securities, and we start off with I equal to 1. So that's just I is security 1. And then in the very beginning, J is also security 1, but then J goes to 2, I is still at 1, and then J goes to 3, while I is still at 1, J goes to 4, and so on until J gets to N. Then we change I to 2, J goes back to 1, and then it goes 2, 3, 4, etc. And then I goes to 3, and J goes back to 1, 2, 3, 4, etc. So you just have to work through this equation. So the first version of the equation, I'm using the covariance between I and J times the weight of I times the weight of J. It may not seem like it initially, but this is the same formula that we had before, except before we only had 2 securities. But for 2 securities, this would give you the same exact result. And then, as always, we could substitute the correlation times the standard deviation of I times the standard deviation of J for the covariance. So this second version of the formula is identical mathematically. Now, as we add more and more securities, the number of calculations that we have to do increases exponentially. And so in the case of 20 securities, for example, the formula that we would have to calculate would have 210 terms in it. And that's as simplified as we can get. And that recognizes that the covariance of I and J is the same as the covariance of J and I. So we've cut out a lot of terms, but we still have 210 terms. So let's take a look at what that looks like. And you can see this is a long formula. And this is with only 20 securities. So you could imagine a large mutual fund might have hundreds of securities in it. And so this equation would be way too large for such a portfolio to even put on this screen in any kind of a readable way. So I'm only showing you this so you get some kind of a feeling for how quickly this equation can easily get out of hand, and that's why we need computers. Okay. Now, imagine that we have a bunch of securities, more than 2. Could be 3, it could be 100, it could be whatever number you want it to be. If we created every possible combination of those securities, so we might have a portfolio that has just security 1 in it, and another one that has security 1 and 2, and then securities 1, 2, and 3, and so on, all with different weightings and everything, we would have an infinite number of possible portfolios. But if we plotted them on a graph, what we would get is what you see here. This is called the feasible set. This is simply the set of all portfolios that can be built. And so the shading that I've used here is supposed to indicate that there's an infinite number of portfolios in there. Now, imagine that you are a financial planner and you have a new client that comes in and you start to review the holdings of this new client, and you see that the client owns portfolio A, which is kind of in the middle of the feasible set. The question is, can you create a better portfolio for this client? Well, what if you think about portfolio B? Now, notice with portfolio B, we have the same expected return as portfolio A, but portfolio B is considerably less risky. That means portfolio B has a better risk-return trade-off, and your client will be happier with portfolio B than they were with portfolio A. How about portfolio C? Well, with C, we have the same risk as portfolio A, but with a higher return. And so that also means that portfolio C has a better risk-return trade-off than portfolio A. So your client should be happier with either B or C than they were with A. And we're going to see here in a minute how to choose where the best portfolio for a particular client is. But notice that both B and C are on the very edge, the upper edge to be more specific, of the feasible set. So you can imagine if you look at portfolio C and A, halfway in between would be some portfolio, call it D, which would be better than A, but not as good as C. Right? So as we keep the same level of risk but move upwards, eventually we get to portfolio C. We cannot go any further than that because further up from C is outside the feasible set. You can't build portfolios with that level of risk and a higher return than C. So B and C are what we call efficient portfolios. What that means is that they have the highest expected return for their given level of risk. Or alternatively, for their level of return, they have the lowest possible amount of risk. That's what we mean when we say efficient portfolios. Now again, notice that B and C are on the upper edge of the feasible set. The lower edge is not good. If you imagine, if you go straight down from C through A down to the bottom of the feasible set, you end up with a portfolio that is not as good as A. So only the upper edge of the feasible set is ideal. And naturally that upper edge has a name. We call it the efficient frontier. And that's because it is the edge, that's what frontier means, is the edge of the feasible set that holds all of the efficient portfolios. Now, at the very beginning, I haven't marked it here, but at the very beginning of the efficient frontier, just a little bit below B, is a portfolio called the minimum variance portfolio. That is the least risky portfolio that you can possibly create. Now, notice that all investors will want to own a portfolio that is on the efficient frontier. Any other portfolio inside the feasible set would be irrational because they could get, for the same level of risk, a higher return on the frontier. So now the question is, how do we identify what the best possible or optimal portfolio is for a given investor? Well, the thing to understand is that investors, like all human beings, seek to maximize their expected utility. Now, remember from your economics classes that this concept of utility simply is a measure of the satisfaction that you get from owning some bundle of goods, in this case, a portfolio. So investors seek to maximize their expected utility or satisfaction. So how do we measure this? Well, in theory, all investors have something known as a utility function. And what the equation here says is that the expected utility is simply a function of the expected return and the variance. Now, this particular way of putting it doesn't specify exactly what the equation is, and there are many, many possible utility functions. So we'll look at one example, just, you don't need to know this, but just so you have some idea of the kind of thing that we're talking about. So what this says is that the expected utility increases as the expected return goes up, all other things being held constant, and it decreases, that's what the minus sign means, as the variance goes up, or standard deviation. Now don't worry too much about the 1/2 times A part. So what A is that's a measure of the risk aversion of the investor. The higher A is, the more risk averse they are. And then the 1/2 is just there to simplify some math that you might do with this. But the key is that expected utility increases as expected return increases, and it decreases as the risk increases. Now, if we took an equation like that and we solved it for the expected return and variance of every possible portfolio, and then we plotted all of the portfolios that gave us the same exact expected utility, what we would find is that those portfolios fall on a curve like you see in the graph at right. So those three portfolios that I've plotted here have exactly the same expected utility for this investor. In other words, the investor would be indifferent between any of those three portfolios. They wouldn't care which one they had. This is called an indifference curve, and that's because they are indifferent to all of the portfolios on that curve. If we took every possible level of utility and we created an indifference curve for it and plotted them all, we would end up with what's called an indifference map. Again, this is simply a graph that shows every possible indifference curve for a given investor. We'll see in a minute that this is the key to finding the optimal portfolio. But before we get to that, realize that the slope of the indifference curve is a measure of the degree of risk aversion for the investor. The steeper the indifference curve, the more risk averse the investor is. So let's look at a chart that shows two different investors. So here we have investor 1 in red and investor 2 in blue. Investor 1 is more risk averse than investor 2. In other words, investor 2 is more tolerant of risk. And you can see for that point that I've diagrammed here, with that level of risk, investor 1 requires a higher return than investor 2 does. That's how we know investor 1 is more risk averse. Now, how do we find the optimal portfolio? Well, again, remember that the goal of the investor is to maximize their expected utility. And what this means is they want to get to the highest possible indifference curve. So what if we took our indifference map that we created a second ago and we overlay it on our chart of the efficient frontier? Well, then we get a graph that looks like this. So here we see investor 1 in green this time. And notice that the first couple going from the left to the right, the first couple of indifference curves are outside of the feasible set. So the investor would dearly love to be on either one of those indifference curves, but they're not feasible. You can't build any portfolios on those indifference curves. So the best indifference curve, or the best portfolio, is the one that lies on an indifference curve that is tangent to the efficient frontier. And in this case, for investor 1, that would be portfolio B. The other indifference curve, the furthest right indifference curve, crosses the efficient frontier at 2 points. And you notice that that has less utility than the second indifference curve. So what we want is an indifference curve that is tangent, in other words, touches at 1 point only to the efficient frontier. Now, what if we look at our second investor? Well, here you see investor 1 that we just saw, except I've eliminated the irrelevant indifference curves. And investor 2, who remember was more tolerant of risk, will have a riskier portfolio, portfolio C in this case. The methodology is the same. We take investor 2's indifference map, we overlay it on the chart of the efficient frontier, and we find the indifference curve that is tangent to the efficient frontier, and that would be point C in the case of investor 2. Now, up to this point, we've only considered risky assets. But what if there was a risk-free asset? Now, let's think about that for a second. What does risk-free mean? Well, risk-free means zero risk. So all risk measures for this portfolio would be equal to 0. So the standard deviation, 0. Variance, 0. Coefficient of variation, 0. Beta, 0. All risk measures would be equal to 0. Now, in reality, there's no such thing as a risk-free asset. But U.S. Treasury bills come very close. And the reason is that there is virtually zero chance that the U.S. Treasury would default on its debts. And the reason is because the U.S. government, the Treasury more specifically, prints money. So if the government runs out of money, all they have to do is print more. And so there's no reason why the Treasury would not make good on all of its obligations. Now, if they print a lot of money, of course, that leads to inflation, and that's a problem. That's a risk that you might not have considered when you bought the Treasury bill. But over a very short period of time, and Treasury bills generally mature in less than a year, so over that very short period of time, inflation generally isn't that much of a problem. So when we talk about risk-free assets, generally speaking, U.S. Treasury bills are what we're thinking of. Now, the rate of return on a risk-free asset is known as the risk-free rate, and that is the minimum rate of return that an investor should demand just for delaying consumption. And let me explain that. So imagine that you have, say, $1,000. You have two choices of what to do with that money. Number one, you could spend it right now, in other words, consume it, or you could invest it. And if you invest it, then you're delaying consumption to some point in the future. And if you invest it without taking on any risk at all, in other words, you use it to buy a Treasury bill, let's say, then the rate of return that you should earn is the risk-free rate. Now, adding a risk-free asset into our mix of risky securities has an interesting effect on the efficient frontier that we're going to see here in just a minute. But first of all, let's talk about the covariance of the risk-free asset with any other security. So here you see the equation for covariance, and we saw this back in chapter 2, so this is not new. And remember, what we do is we take each security minus its expected return times the other security minus its expected return, and then multiply that by the probability and sum them over all possible outcomes. Well, in this case, the second security is the risk-free asset. And because the risk-free asset has a variance or standard deviation of 0, that means that its return is the same in every possible state of the economy. And if the return never changes, then each possible return is the same as the expected return. And so that second term will always equal 0. 0 times anything is 0. And the sum of a whole bunch of zeros is 0. Therefore, the covariance of any asset's returns with the risk-free asset must be 0. Also, the correlation will always be 0 between the risk-free asset and any other asset. So remember, the correlation is the covariance divided by the product of the standard deviations. And if that numerator is 0, then the correlation must be 0. There is a little problem with the fact that in the denominator, the standard deviation of the risk-free asset is 0, and so you get a 0 denominator. But by assumption, the correlation is 0 because the covariance is 0. This very special property of the risk-free asset leads to some interesting outcomes. Let's look at what happens if we build a portfolio that includes some asset 1, we'll call it, and the risk-free asset. So here's our portfolio standard deviation equation. The second asset is the risk-free asset. So we have the weight of asset 1 squared times the variance of asset 1 plus the weight of the risk-free asset squared times the variance of the risk-free asset plus 2 times the covariance of asset 1 with the risk-free asset times the weight of asset 1 times the weight of the risk-free asset. And we take the square root of that whole thing. Well, we just got done saying that the covariance of the risk-free asset with any other asset is 0. So that third term just goes away. We also said that the variance or standard deviation of the risk-free asset is 0. So now the second term goes away. All we're left with is the weight of asset 1 squared times the variance of asset 1. And if we take the square root of that product, we get the standard deviation of the portfolio is just the weight of asset 1 times the standard deviation of asset 1. Now, I notice I have in my formula there, I have the weight of I, but that should be 1. So the interesting thing here is that the risk of a risk-free asset and some other asset portfolio is simply a linear combination of the weight of that first asset with its standard deviation. In other words, it's linear. Now remember that the expected return is a linear function of the expected returns of the assets. So when we combine the risk-free asset with any other asset, the combinations must fall on a straight line. So we'll see that next. So here we have again our efficient frontier, but this time I've added a risk-free asset, which because it has no risk, it plots on the y-axis. And if we combine the risk-free asset with the minimum variance portfolio, all combinations of those two securities must fall on that straight black line there. Notice that all combinations of RF and the minimum variance portfolio are outside of the original feasible set. So what we've really done here is we've expanded the feasible set. This line, by the way, is known as a capital allocation line, or a CAL. And again, all possible combinations of the risk-free asset and the minimum variance portfolio are somewhere on that line. Now, there's no reason why we couldn't combine the risk-free asset with any other portfolio on the efficient frontier. So let's see what happens if we combine it with portfolio B. Now we get the green line, and notice that any portfolio on that green capital allocation line is better than any portfolio on the original capital allocation line. So there's no reason for any investor to invest in a combination of the risk-free asset and the minimum variance portfolio, because they're better off if they invest in a combination of the risk-free asset and portfolio B. Well, as I said, we could continue on like this, combining the risk-free asset with every portfolio on the efficient frontier. And if we do that, ultimately what we're going to find is that there is one capital allocation line that is steeper than all of the others, and furthermore, it will be tangent to the efficient frontier at some point. And we call this steepest possible capital allocation line the capital market line, or the CML. Notice that it is tangent to the efficient frontier. You cannot create a capital allocation line that is steeper than this, because that would be entirely outside the feasible set. So the capital market line gives us the best possible risk-return trade-off. And because of that, as we'll see in a second, all investors would want to own a portfolio somewhere on the capital market line. Notice also that portfolios on the capital market line are in every case better than any portfolio on the efficient frontier. That is, you get a higher return for the same level of risk. Now, that portfolio M that lies at the tangency point of the capital market line and the efficient frontier is a very special portfolio. We call that the market portfolio. So this portfolio M is a collection of all risky assets. So notice that at the risk-free rate, that portfolio there, that is 100% in the risk-free asset. Portfolio M is 100% invested in risky assets. It does not hold any risk-free asset. But every other portfolio on the capital market line is some combination of the risk-free asset and the market portfolio. And the more tolerant an investor is of risk, the further up the capital market line their optimal portfolio will be. Now, portfolios that have a long position in the risk-free asset and the market portfolio are known as lending portfolios. Now, why is that? Well, think about it. We said earlier that the risk-free asset effectively is a U.S. Treasury bill. So when you buy a Treasury bill, you are lending money to the U.S. government. So any portfolio that's on that first section of the capital market line involves some allocation to the risk-free asset, some positive allocation to the risk-free asset. And so those are all portfolios that involve lending money to the U.S. government. Now, the question is, how do you get beyond a 100% investment in the market portfolio? In other words, the red point there. Well, you do that by short selling the risk-free asset. And if you're not familiar with short selling yet, what that means is that you go out and you borrow a Treasury bill from somebody and you immediately sell it. Now, when you do that, ultimately, you're going to have to replace that. So you're going to have to, at some future point in time, you're going to have to buy that treasury bill back and give it back to the person that you borrowed it from. This is all perfectly legal. But when you short sell the risk-free asset, what you have is a negative weight on the risk-free asset. So effectively, you are borrowing money at the risk-free rate. And that money will be invested in the market portfolio so that you can get beyond portfolio M on the capital market line. And so a portfolio up there, let's say where the G in borrowing is, that might be negative 50% in the risk-free asset and 150% in the market portfolio. And the further you go up the capital market line, the bigger that negative weight on the risk-free asset is. What does the capital market line tell us? Well, it tells us what your required return should be for an asset with a particular amount of risk. And in this case, we're talking about total risk or standard deviation. So let's figure out the equation for the capital market line. So if we write this in slope-intercept form, and remember, slope-intercept form is just the basic equation of a straight line, y equals mx plus b, where m is the slope and b is the intercept. So looking at this graph, you can see immediately that the risk-free rate is the intercept of the capital market line. That's the y-intercept. That's where the capital market line crosses the y-axis. And then the slope, remember, is the rise over the run. And so in this case, at portfolio M, you can see the rise is the expected market return minus the risk-free rate, and the run is the standard deviation of the market minus 0, which is just the standard deviation of the market. So the equation for the capital market line is given here. This is the risk-free rate plus this term in brackets, the expected market return minus the risk-free rate divided by the standard deviation of the market. That's the slope, all multiplied by our x variable, which is the standard deviation of the portfolio. Now, by the way, let me remind you that one of the nice things about straight lines is that the slope is constant. The slope never changes, unlike with a curve. And so the slope of the capital market line is the same at every point. Now, that slope is known as the market price of risk. What it tells us is the amount of excess return, that means over the risk-free rate, that you can get per unit of total risk. So the excess return divided by the total risk. Now, remember that the capital market line is tangent to the efficient frontier. And what that means is that the slope of the CML and the slope of the efficient frontier are the same at point M. Now, hopefully you remember from every math class that you've ever had, when a curve and a line are tangent, that means the slopes are the same. And when you have two things that have the same slope, what do? Well, we always set them equal to each other. And in this case, if we do that, if we set the slope of the capital market line equal to the slope of the efficient frontier, and then solve for the expected return of the portfolio, something interesting pops out. That is the capital asset pricing model. And you should be familiar with the capital asset pricing model. That says that the required return on some asset is equal to the risk-free rate plus the asset's beta times the market risk premium. So that's where the CAPM comes from. Sometimes it seems like people think the CAPM was just invented on its own, but it's a mathematical result that comes from this idea of the efficient frontier and the capital market line. Here's the graph. Now, remember that with the security market line, that's just the graph of the capital asset pricing model. We talked about this in Chapter 2. The CAPM and the SML are precisely the same way, or same thing. When we graph it, we call it the security market line, and when we write out the equation, we call it the CAPM, but they're the same concept. Also, note something very important here. The risk measure in the capital asset pricing model or security market line is beta, that is market risk. If you remember, with the capital market line and the efficient frontier, the risk measure was total risk. So if you see a graph that looks like this and you have to identify it, you need to look at what the risk measure is. If the risk measure is beta, you're looking at the security market line. If the risk measure is standard deviation, then you're looking at the capital market line. And that's something that often confuses people. Now, the CAPM is just a model, right? It's a mathematical way of trying to predict what the required rate of return should be. And it's based, as all models are, on a set of simplifying assumptions. The world is simply far too complicated to come up with a simple equation that could be used to model just about anything. And so almost always models have a set of assumptions behind them. And the same is true of the CAPM. So let's look at those assumptions. There are 9 of them. So the first one is that it is a single period model. That means there's a beginning period and an end of that period, and nothing can happen in between. Because if you are allowed to change the quantities of your holdings or anything in between the beginning and the end, that would complicate things immeasurably. Secondly, we assume that investors seek to maximize their expected utility, which is based on expected return and standard deviation. When we looked at that utility function a little while ago, that's exactly what we said. We said that expected utility is a function of expected return and standard deviation, and that the goal of any rational human being is to maximize their expected utility. Next, we assume that investors can borrow and lend unlimited amounts at the risk-free rate. Remember, that's how we move up and down the capital market line, is by borrowing or lending the risk-free asset. Next, we assume that all investors have the same information and that they draw exactly the same conclusions from that information. We call this homogeneous expectations. If we didn't have this assumption, we would have to have a different model for every single investor, and that simply would be impractical. Next, we assume that assets are perfectly divisible and liquid. That means that you can own fractional shares of stock. You might own a quarter of a share of IBM, for example. Now, in reality, you can't do that. But we have to make a set of simplifying assumptions. So if assets were not perfectly divisible, then our capital market line and our security market line might not be continuous lines. They might be like dashed lines or something. The next assumption is that there are no taxes and no transactions costs. This is called frictionless markets. And the reason is that taxes and transactions costs make the markets not work perfectly. So you can imagine why. With taxes and transactions costs, then arbitrage might not be able to bring prices exactly in line with where they should be. If you're not familiar with arbitrage, that's simply making a transaction that has no risk but a greater than the risk-free rate expected return. And so if taxes and transactions costs exist, then prices in two different markets, which in theory should be the same, may not be, because investors can't buy in one and sell in the other until those prices are the same, because taxes and transactions costs would keep them from being able to do that. Next, we assume that all investors are price takers. Basically what that means is that no one investor is big enough on their own to set prices in the market. Now, in reality, there are a few investors that possibly could set prices, or at least move prices a little bit by taking a big position. But again, we have to simplify the world, so we assume that all investors just take whatever prices are available. We also assume that quantities of securities are known and fixed. That has to be the case because, remember, back to the very first assumption, we assume it's a single period model, so nothing can change between the beginning of the period and the end of the period. And then finally, we assume that the market is in equilibrium. That means that expected returns equal required returns. Prices are in balance. Whenever you have a model, particularly if it's based on some set of simplifying assumptions, you need to test that model to see if it really works in the real world. So one of the things that people do is they look at the assumptions behind a model, like we just saw, and they say, well, those assumptions are unrealistic, therefore this model can't possibly be any good. Well, it may be that the model is no good, but it might be that despite all of the crazy assumptions, the model works pretty well in the real world. And so we want to test based on this. And there are a number of things that we can test when it comes to the CAPM. So first of all, according to the theory, beta, the market risk measure, should be stable over time. So in other words, if you looked at the beta of a stock 5 years ago and you looked at it today, in theory, it should be the same. Now, what we know from testing this is that betas change all the time. More specifically, what we find is that betas tend to move towards 1. So stocks that have very high betas right now, in the future, will probably have lower betas that are closer to 1. And 1, remember, is the average beta in the market. So high beta stocks tend to see their betas drop over time. And stocks that have low betas tend to see their betas increase towards 1 over time. This is called mean reversion. And this is a flaw in the theory of CAPM because we find that this doesn't actually, that beta isn't actually stable over time. Now, a second test that we could do is we could look at the slope of the security market line and test to see if it's positive. Now, remember, we talked about this back in Chapter 2. We said that we always assume that investors are risk averse. And that means that they would not make an investment unless they expected to get a higher return if they take more risk. And so that suggests that the security market line should have a positive slope. And in fact, that's generally what we find. There are periods of time that you might look at where that's not the case, but almost always that is in fact the case. So that's one in favor of the CAPM. Next, we could test to see if the security market line, or the CAPM, is in fact linear. The alternative would be that it would be some kind of a curve. What we find, fortunately, because nonlinear functions are much harder to model, what we find is that the security market line is pretty much a linear function. Finally, we can test to see how well the CAPM or SML works for all kinds of assets. So generally when we talk about the CAPM, we talk about stocks. But in theory, it should work for any type of risky assets. Well, it turns out that that's not necessarily true. For example, it doesn't work particularly well for bonds. Okay, I think that'll do it for Chapter 3. We'll take a quick look in the next couple of minutes at the mini case from Chapter 3, but there's not a whole lot other than theory in that mini case. There are some calculations that can be done, and we'll take a look at the spreadsheet for that, but mostly it's just answering a bunch of questions. So as always, please make sure that you work through the mini case, and we'll take a quick look at my spreadsheet for that, and then we'll be done for this lecture. Okay, I wanted to take just a couple of minutes here to go through the spreadsheet that I have available for the Chapter 3 mini case. And we've pretty well been through all of the questions in the mini case during the lecture. And as always, I encourage you to work through that mini case as a practice for the homework and for the exam. It starts out asking about two securities, A and B. A has an expected return of 10% and a standard deviation of 20%, and B has an expected return of 16% and a standard deviation of 40%. And they tell us that we're going to build a portfolio that's 30% in A and 70% in B. And so if we calculate the expected return of the portfolio, that's simply going to be 0.3 times 10% plus 0.7 times 16% gives us 14.20%. The standard deviation, remember, is a little bit more complicated, and they've told us here that the correlation coefficient between A and B is 0.35. So that's about an average correlation for stocks in the U.S. market, and it's low enough that we should see some substantial risk reduction when we combine these together. So if you do the calculation, what you'll find is that the standard deviation of the portfolio is 30.62%. Now, let me point out something that's important. because you notice that that 30.62 is kind of in between the standard deviation of A and B. So first of all, whenever you combine two securities together or more, you don't always end up with something that's less risky than all of the securities in the portfolio. Sometimes you do, sometimes you don't. To a large degree, that depends on two things: the weights that you choose and the correlation between the securities, or if you have more than two, the average correlation between the securities. And so with this particular set of weights and correlation, our portfolio has a standard deviation kind of right in between the two. However, notice that we have 70% of the portfolio in investment B. So if we were to calculate a standard deviation as a weighted average, do not do this, right? I'm just showing this as an example, but if we did, we would say 0.3 times 20% plus 0.7 times 40%. Notice that we would get 34%. The actual standard deviation, the real one, is less than that. So we're getting a better risk-return trade-off with this portfolio than we would if we just ignored the correlation, which, again, don't do this. You're not allowed to do this, but this is kind of a benchmark. So we are, in fact, getting some risk reduction here. Now, the mini case also asks you to calculate the standard deviation of a bunch of portfolios that are combinations of A and B with that 35% correlation. And you can see I've actually done it here with a 0.35 correlation and a +1 and a -1. And I've calculated the standard deviation of the portfolios with a bunch of different combinations of weights. So we start off with 100% in A and 0% in B, and then 90% in A, 10% in B, and so on. Remember that the weights have to add up to 100%. Then I've plotted these, and you can see the charts right below there. And just like I showed you in the mini case, when the correlation is +1, every combination of A and B lies on a straight line. If the correlation is less than perfect positive, in other words, +1, then the combinations of A and B will start to bow out towards the northwest. That's the indication that you're getting a better risk-return trade-off by combining A and B together. And when the correlation is -1, perfect negative correlation, you notice that we get pretty much a risk-free portfolio at some weight setting. And that the weights there are around 70% A and 30% B. It's not exactly 70-30, but it's very close to that. Then the mini case asks us to add a risk-free asset into the mix. And so what I've done down here at the bottom is I've combined security A with the risk-free asset, and I've calculated the expected return and standard deviation of a bunch of portfolios. So just like before, I start out with 100% A, nothing in the risk-free asset, and then 90% in A, 10% in the risk-free asset, and so on. And you notice in the chart, just like I told you in the lecture, that all combinations of A and the risk-free asset fall on a straight line. This would be true if I combine B with the risk-free asset, or any combination of A and B with the risk-free asset. The reason for that, remember, is that the correlation or covariance of the risk-free asset with any other portfolio is 0. That's a very important point. Now, on the second worksheet in this workbook, I wanted to show you, this was the little movie that I created, and I've implemented it in Excel. And so what I have is I have A and B, and then you can change the correlation by using the slider down here right below the graph. So right now, the correlation is set to 100%, and all combinations of A and B fall on a straight line. But if I change the correlation to 80%, you notice that it starts to bow out. And if I go to 60%, it bows more. Again, notice that point A and point B do not change. They don't move because this is 100% in A and this is 100% in B. It's only the combinations that change when the correlation changes. And so the lower the correlation, the more it bows out. And when we get to a correlation of -1, you see, just like in the little movie in the lecture, we get a risk-free portfolio. All right, and then finally, I've kept in here the Chapter 2 mini case data from an older edition of the textbook. So we no longer have this in the textbook that you're using, but it's good data. So what we had here was we had a probability mass function for Treasury bills, Alta Industries, Repo Men, American Foam, and the market portfolio. And they asked you to calculate the expected return, the variance, the standard deviation, the coefficient of variation, and the beta of each of these securities. So I encourage you to work through this. Now, remember that you may not understand the formulas that I've used in Excel to do this, but you should be able to do it by hand. Now, below that, I have the variance-covariance matrix and the correlation matrix. These are just convenient ways to display all of the covariances or all of the correlations. And actually, they're a little bit more than that because we can use these to calculate the portfolio standard deviation. So there is a way to do it using matrix algebra, which we're not going to get into for this class. But the variance-covariance matrix and the correlation matrix can be very useful for that. And then below there, I have various combinations of Alta Industries, Repo Men, and American Foam, and then I calculate the expected return of these portfolios and the standard deviation, and I've plotted them, and you can see the efficient frontier and the feasible set and the individual securities and portfolios that plot in there. So this is just some extra practice problems that you can do. Okay, I hope that you found the lecture to be useful, and I will see you next time with Chapter 6.